Welcome again to the NPTEL course on storage systems. So, in the previous class we had some general discussion on device drivers. We will go into some more details in this class, and also we will look at an example. I think again, to summarize a bit, there are many ways to access devices in many systems including Linux. We have what are called CAR devices, CHAR devices, people pronounce it differently. Basically these are what are called non-block based devices. Basically it is a stream, okay. So they do not have any markers, it is basically a stream, okay. Or you can also do control operations on it. Block based devices on the other hand have very clear markers, when some block starts, when it ends. For example, 512 bytes or 4 kilobytes, whatever, right. There is a definite beginning to the block and end to the block, and it is the information is structured in terms of blocks, okay. And typically the system caches the blocks, okay. The basic reason is that when you are dealing with blocks, the reason why you are dealing with blocks is because of addressability considerations, because you want to access a very large stuff. If you access at smaller levels, you need the addressability is going to be not enough. So therefore, because you are dealing with such things, it turns out that you are dealing with typical slow devices, and therefore caching also helps here, okay. And typically most file systems are expected to be running on top of such block devices. You also have things like network devices. Oftentimes it is not exported out as a device that users can use directly. They are usually accessed in kernel mode. What I mean by that is, if you have a disk, for example, it can be exported as /dev/disk1 HDA, okay. And if you are a user program, of course it could be a privileged user program, okay. For example, a process that is owned by root, say root also is a user in the system, and user also can start a process on the console or wherever, right. So any process that he starts has got root privileges, but it's still a user program, it's not a kernel code, okay. It's still using system calls and other things, okay. Now if you look at block based devices or character based devices, most Unixes and Linux, they will export that particular device as some /dev/HDA whatever, okay, TTY, etc. That means that a privileged program which has enough privileges to open the device can directly read and write, okay. That means a user program that is without any kernel code, okay, can directly access that particular device. Whereas the network device, what is being mentioned here, most like in kernel mode, means that you have to have your code if you want to access these things inside a kernel itself. That is what is mentioned. Of course, some operating systems, they expose network devices, even protocols outside. There is a operating system called Plan 9, some of you might have heard of it. It exports even TCP. You can access it as /dev something /TCP/IP, etc. Okay. You want to read from a TCP, this one you can say read from /dev something TCP, etc. Okay. That is the way to do it, okay. Typically devices are identified by some major and minor numbers. Why do we need all these major and minor numbers? Basically because you want to keep the system dynamically configurable. So you are not really constraining system to have exactly this number of devices. So if you do not know what device are going to put and taken off, right, you still want to refer to them, right. So suppose I am able to say that when I attach a device, I give it some number as a part of attaching a device, electrically attach it, but then I say, now that I attached it, please give me a corresponding, let us say, way to access the device. The simplest thing that people have figured out is giving it something like a major number. So for example, I can say that my tape device has got major number 7, let us say. It can use it can use that number as a way to say that I am interested in tape number 7. Suppose I take the device off, okay. Let us say I have maximum, let us say my major number is let us say 8 bits, okay. That means I can have a maximum of 256 types of devices, and then I can later, once I remove 7, the tape device, I can attach some other thing like a CD-ROM for example, and say reuse that number slot 7, okay. I can do those kind of things. So, you can always say why not use some user friendly names, okay. You can always have user friendly name, but you have to parse it again. You have to parse it, and again it takes time. So, the idea is to avoid those things so that you have some numbers, so it makes it easier. Okay. Just like file descriptors, if you are familiar with file descriptors, you will notice that once you open a file, you get a file descriptor. In the beginning at open time, you parse it, the full file name, slash something, slash something, slash something. That takes some time, okay. And then once you get a FD, then you do not have to go through the process. So that is basically what is being done here. The minor numbers are, you can have many types of units of the same type. For example, I have a tape controller, I might have lots of tape devices. So, tape controller might have a major number, and the tape unit itself might have the units have that number. For example, if you take a regular audio system, right, it has got 2 tape drives, right, we can call it tapes. You might have one controller and have 2 tape drives, okay. The one which does the recording, one which just plays, okay, or one which does both recording and play, one only plays, okay, whatever, right. So, the minor number tells you how many things. So, you can have a big system with 1000 disks, okay. Impossible that you can identify each disk by its minor number, that also is possible, okay. So, it is unit identifier. So, normally when you have a, so the example I am going to discuss today is a character device, or okay, and typically if you are talking about a character device or non-block device, you need to provide the following things: how to open it, how to open the device, close the device, how to do I/O on it, okay, and how to do some control operations on it. I/O-CTL means I/O control, means you are trying to control how the device operates. Okay. So, for example, somebody might want to try to do something slightly non-standard with the device. Okay. Let us say, for example, the block size is something on a particular tape, and you want to change it to some other thing. Let us say, I am just giving a random example, and I/O-CTL may be used to configure that part. Essentially, you can use it for configuring the device, okay. Or it could be that there are some interrupt lines, you want to tell it to use a particular interrupt line, because on the system the typical interrupt line it is using is being used by somebody else, and I want to say what you typically prefer is not available, use something else, who knows, those kind of things may be possible, okay. There is also memory map operations. I think I will skip this right now, okay. So, typically a character device driver registers itself with register character device major operations. Basically, what is it? You are basically saying at this particular major number, there is going to be a device whose operations are given by a vector of operations, okay. And these operations are typically what we discussed before: open, close, read, write, etc. Okay. To give an example, we can look at this one. So, this is an example, okay. We are talking about something called, what I am discussing here is what is called as pseudo device driver INTS, interrupts. What is pseudo device driver? There is actually no real device there, but I am giving you some way to access some information which is not otherwise accessible, okay, what is in the kernel, okay. So, I am going through an interface, the interface gives me some information, in a structured and in a very safe manner some information that I can get from the kernel. What is the information I am looking for here? I want to collect a trace of interrupts in each CPU. In a real system, right, there are a lot of interrupts going on, and let us say I am talking about a multi-CPU system, interrupts are going on all the time. Okay. I want to write something which enables me to have a trace of the interrupts. When did this interrupt come in? Okay. Which CPU handled it? How long did it take for it to handle it? Okay. For example, I want to know information like when does the time of the interrupt, which CPU got interrupted, when was the time which this time of the interrupt, is it the entry time or the exit time, okay, and the interrupt number. Basically I want to count. Okay. Interrupt number means I want to start with 1, 2, 3, 4, I just want to keep track of it. Okay. So this information is typically not available to you typically. Okay. Probably some crazy operating system will give you this, but usually nobody does it. Okay. But this information available in the kernel, somewhere it is there. Question is, how do I get this out? Okay. That is the question. So what we are going to do is we are going to devise a pseudo device driver which can be loaded onto the system. Now who can load the system? Who can load this device driver? Only a authorized person, a person who has appropriate privileges. Any random person cannot do it, because this code that you are executing is sensitive. Okay. You can essentially, when you insert this particular code in the kernel, you have access to the kernel data structures. You can clobber it, you can change it, you can read from it, okay. You can do various things. Okay. Now that is a bit, let us say you are giving a lot of privileges to somebody, okay, and it can be it can really mess up things. So that is the reason why it has to be done by privileged parties, okay, and that is why it is if a privileged party can load this particular pseudo device driver, then what you have to do is you should be able to register that device, okay, and then that operations corresponding to the device has to be set up. Okay. So what we are going to do is we are going to register the device, and then I am going to say that please make sure that when I say read, actually you mean this. So let us look at that again. So this example, what we are doing is we are going to do, when you load the things, we are going to do init module. Okay. That piece of code that is going to be put in the kernel is going to initialize something. Okay. Now this is basically a lock that is required, and that is going to be initialized. Okay. This is not, no mutual exclusion is being done here. It's just, you are just taking something called a spin lock, and that is being initialized, right? Just initialization. And what we are going to do is this particular init module is going to do this registration here, and it is saying that take 233 as the major number. Int s is the name of the, you can give it any name you like, okay, it is just for our convenience. Okay. And it says and int f ops. What is it saying? It is saying that for this particular device, give me match up with these particular operations. So what are the operations here? These are the operations here. So there is int f ops right here. Okay. You are basically saying that on this device, whenever somebody says read, it actually I mean int as read. Okay. Basically, it's a function pointers. Okay, you are installing these function pointers. Normally, it will be some function pointers which is with no valid information in the beginning. Okay. Once you load it, these function pointers will be initialized to these values. Okay. So whenever I say read on this device, I am asked to go and read int s underscore read. Whenever I say write on the device, because I will have a device by the name slash, let us say slash dev int s, let us say. I can open it. I can, just like you can read and write, right? I can also say read from that slash dev int s. Okay. Then I am going to read from corresponding thing is going to be done int s. Okay. So, and this particular driver is going to supply these routines, int s read, etc. For example, here is a place where int s read is there. Here is a place the write is gone. Okay. So basically, I am going to register the device, and then I am going to give it a name major number, and I am going to set a corresponding routines for what I mean by read, write, etc., open, close, all those things, and that is being decided by this set of function pointers. Okay, and that function pointer is being defined here. Okay, file operations, file underscore operations. This part is being done. Okay. Okay, you can see that it's doing some additional things also. In addition, because these are some special things, because we are doing interrupt counting. This is something unusual for this particular driver. Not every driver will be doing these things. So it has got other additional functions. Okay, and what is that? And that I am going to initialize. Okay, it turns out that p-enter IRQ is the name of the function that is called by the kernel on entry of the interrupt, and it is user specifiable. Usually if it is null, nothing happens. Usually that's what could be happening. Okay, p-enter IRQ is some kind of a pointer that is sitting there. If it is null, nothing happens. On entry into the interrupt, nothing happens, and when you execute, nothing happens. No extra code is executed. But if you want to take control of what happens when interrupt happens and interrupt leaves, then I can provide a function pointer, right, saying execute this code. When you enter the thing, exit out, you execute that. And that I am also doing here. Okay. So I am saying p-enter IRQ is enter IRQ. So this is what the kernel is going to call, but now I am defining it to enter IRQ, and this enter IRQ is basically here. I am defining them here. What it means is that on entry of whenever interrupt handler starts execute, you first execute this part, okay, before it does its processing. Okay. It does its processing and it does its processing, whatever minimal it does, and then it calls this function. Okay, right. So similarly, when it wants to leave, it does some processing and calls this. Okay. So again, you have to look at it very closely. I sort of might have made it slightly set things slightly in the different order than actually should happen. Normally what will happen is on interrupt entry, you do some processing, then you call this function. On interrupt exit, you call this p-enter exit, okay, p-enter leave, p-leave IRQ, and then do the thing that the system does. Okay. So anyway, all I am trying to say is that there are functions that are available that can be executed on every entry of the interrupt, and there is a function that is available that can be executed every time you leave it. And now I am defining it also. So this module is going to define what has to be done. There is also something called CLI here. All these things are old stuff. Current Linux kernels will not support these things. Okay, you have to be careful. Everything keeps changing. Okay, so this basically says shut off all interrupts all over the system. Because this is a sensitive thing, I am trying to get control about what should happen on interrupts. And if interrupts happens while this is going on, there can be some mess. For example, it could be that interrupt happens just in between. Okay, so there could be some messy situations developing which you don't have any control over. So I am saying here, shut off all interrupts across all the processors. Once I have safely set it properly, then only. Notice that a CLI will not return back until any interrupt that's already happening at the time this call was made, right? They had to be completed before CLI will come here. Okay, anything that's happening at the time when CLI is called in other CPUs, all the interrupts have to be completed. Then only the CLI will return. Therefore, you are in a completely clean state. So you can do these things without too much headache. Do it properly. Again, STI also will saying it's enable interrupts now. So now all interrupts are now enabled. Okay. Okay. So this is basically what init module does. Similarly, there's a cleanup module. Okay. So that will essentially say that if you have been recording so far, okay, stop recording. Okay. So recording is a variable in the driver. We define it here. Okay. And basically this says that whether the recording is going on or not. That means I am tracing the interrupts. Okay. So when I am leaving, in case it is still on, so this cleanup can actually happen asynchronously. Why? Because the root is sitting there and the guy says shut down the device. So you already set the recording going on, and for some reason I had to shut up, I said shut the system completely, right. So I have to clean up the module. I have not done the proper job. Normally what would happen is that I take care of this properly, okay. I am recording it, I stop it, etc. But sometimes the administrator can, without telling me, can shut it off also, okay. So that's what is being, so basically I am trying to see if somebody's, while the recording is going on, somebody says clean up, I am going to do this, okay. So you will see that there are some routines like int_s open, int_s release. These things do nothing, okay, because the pseudo device driver, nothing is to be done in this case. Sometimes nothing happens, okay. You can also unregister, basically saying that I don't need this device any longer. Please, you can go ahead use this major number for somebody else. Usually the major numbers are limited because I mentioned it can only be 8-bit quantity. So you might have 256 devices. On a large system, 256 devices may not be sufficient. Okay, that's why you might want to use it. As I mentioned, devices are accessed by user mode programs by accessing special device files. As I mentioned, it's like /dev ints. Okay, that is and I can open it by user mode programs. Of course, as I said, it may need to have privileges. Okay, user mode programs special access. The inode says that they are special device files. If you look at it, /dev ints is what's called a special file. It's not a regular file. Okay, and there's a metadata that's kept for each of those things, and the metadata will basically call inode, snode, sometimes called snode. That will have information saying that it's a special device file. It's not a regular file, and in that particular inode, it will have all these details. What is the major number, minor number, etc. Okay. Again, on any of these devices, on open, the corresponding open method is called. In our case, it's int_s_open, because that is when you load this device. The open method again is now essentially the pointer that is going to be there actually is int_s_open. On close also same story. Again, the important thing to notice is that open called only on the file object creation, not on dupes. Basically, only when the object is created do you call it. If some other party also calls at the same time, right? If it's already open, you just return back saying it's open already and give the FD. Okay, so you don't do it on every single thing. For example, you know that there is something called a dupe operation in a file, right? So you can duplicate the file descriptor. Now you're not really creating an object afresh, so you don't have to really do any specific operation for setting the device up or the file up. Okay, so on duplicating FDs, you don't need to do anything special. So that's why even if you call open on such FDs, nothing happens. Okay, similarly close, you can close something many times. There is some kind of reference count kept, and then the last final call of the close when every other reference is gone, right? That's the one HL which does the file object relation. Okay. If you have read and write, you typically pass a pointer because there's an implicit pointer. Some of you might know that when you do read and write, there is an implicit pointer which says where you have to read from and where you have to do the write. Okay, so you have to pass this current offset, and that might have to be updated. Okay. Again, if you do an LSEG, you have to check whether the LSEG is offset. Okay. Now let's because we're doing the interrupts example, let's just revise something we know about interrupts. Interrupts can interrupt anytime. When CPU is in normal user mode, that is, my user program is running, your browser is running, for example. Even if the CPU is in the kernel mode, okay, it's because of a system call, it can get interrupted because the interrupt is coming from hardware. In our pseudo device driver, we don't really have any hardware interrupts for our pseudo device driver, but there are interrupts coming in from other reasons, other devices, which other device drivers are handling. Okay, because on this system there will also be timer interrupts, which is being handled by some other part of the kernel code. Okay, but we are talking about a pseudo device driver, which we are writing, but that itself does not have any hardware interrupts coming in. Okay. There is no hardware corresponding with pseudo device. Pseudo devices do not have a corresponding hardware, whereas real device drivers have a corresponding hardware device. Okay. An interrupt execution of CPU can be interrupted by another different interrupt. For example, oftentimes the TTY interrupt is considered low priority, while the TTY interrupt is getting serviced, a disk interrupt or a timer interrupt can come in and take over. Okay. So sometimes what happens is that I have multiple devices, disk devices, and multiple disk devices, and one interrupt is being handled. Another disk drive also interrupts now. Okay, and these guys are at the same privilege. So what you will do in that case is you will first run the first interrupt to completion before you get the second guy going. Okay, that's what you say. Okay, it can get interrupted, or you complete the current thing, whatever is happening, then only run the next guy, because they are at the same level. You can raise a soft interrupt, that happens through system calls. Okay. Process context is assumed only when all interrupts exit. Okay, that is, you go back to user space. Basically, the interrupt controller and CPU. Interrupt controller basically manages interrupts, and the CPU gives abstraction of IRQs. And these are the things that the kernel actually deals with. Okay, because these two things are hardware related things. Each device driver sets an IRQ handler and programs the device to interrupt at that IRQ. Okay. So when the interrupt comes in, you are supposed to execute that interrupt request handling. Okay. And this request IRQ, free IRQ are the functions for registering this IRQ handler. And we are not using any of this in our driver because we do not have any real hardware devices that are interrupting us in our pseudo device driver. Okay. We do not have these things here. IRQs can get routed to any processor. Okay. And usually the interrupt controller bans the load. Basically, in most Linux systems, in the past it was not done, but in the recent past, you will find that the interrupt load is handled by all the CPUs. So it gets routed. But an IRQ will only run only on one processor at a time. Okay. But you can have different interrupt request processing going on different cores at the same time. Okay. And if they are touching the same data structure, then they better synchronize among themselves. Okay. IRQs can serialize other processes with spin blocks. Okay. Normally, interrupt request handling routines cannot sleep because it interferes with proper functioning of the system. Because once you sleep, the possibility is that some code is buggy and you forever sleep. Okay, that is possible. There are many other reasons also, latency, etc. Okay. For that reasons, you usually don't allow interrupt request handling because it's happening the highest priority. So it's happening the highest priority. If that guy is going to sleep for something, for some reason, okay, the whole system essentially is in a delicate situation now. Okay. So normally you can, if you have to do any serialization with respect to access to a particular data structure, the way to do it is to spin lock. That is, you don't, basically the idea is that each of these IRQs are short running programs, short running code, piece of code, and they will, being good citizens, right, they usually do their job and run out quickly. So you can actually afford to spin lock. You are using up that CPU a lot, but since you are doing it for very short periods of time, it doesn't matter. That's the idea. Okay. So there are things like CLI/ST I already mentioned. It disable and sets interrupts on all processors and returns only after all currently executed interrupts are completed on all processors. Okay. There is also a disable. Okay. Disables the IRQ only and returns only after this IRQ is complete executed. Okay. Other thing is, in addition, process and interrupts are also concurrent. Okay. So not only interrupts, but it can interfere with regular execution. So you need mutual exclusion. I already mentioned spin locks. Okay. You can also wait for events, synchronization for example. There are various types of ways to synchronize using sleep logs, condition variables, semaphores. These things sleep, so this cannot be used by interrupt handlers, but they can be used by regular kernel code. It's possible. Okay. You can also have interruptible and non-interruptible sleep. You get into non-interruptible sleep and some very delicate situations, but the thing is, if it never gets woken up, that interrupt doesn't, if that you cannot ever break that sleep, right? The system might hang. Okay, that is also possible. You have to be careful about this. Again, I'm not going to do details about this, but just I just wanted to be aware of this. Okay. Again, you want to sometimes access user memory in the driver. Now it turns out when you want to access some user memory from the driver, because the driver code is running in the kernel, because you installed it inside the kernel, it may refer to some data that's available in the user space. That is a slight delicate operation, because the kernel code is all powerful. Because it's all powerful, you can access things which normally I can be allowed to access only with some care, right? That means that if the user gives me some invalid piece of data, okay, if the kernel doesn't check that it is invalid, okay, and goes and accesses it, then there will be a violation with respect to whether with respect to the validity of the data, okay, and the kernel can get into a complicated situation. Now it is now suffering on account of user giving wrong information. Okay. Typically, you want to avoid those kind of situations. That's why you need to go through specific routines. For example, there are something called copy from, copy to user. Copy from user means you copy, there's a buffer given by the user, you carefully select it, look at it, see if it's okay, and then after convincing yourself that everything is fine, that all the data that the user is giving is valid, then you copy into kernel buffer. Similarly, you can get user and put user just for the instead of, for example, at a character level, for example. We'll come to this. Okay. Why do we need to use these things? Because I might ask you to, I might send some parameter to the driver. Let's look at one example. Okay. Here is a case where I have a device. What is the device doing? It is /dev/ints. What is it doing? It is collecting traces of interrupts. Which CPU is getting interrupted, at what time, etc. Now you can't, once it starts, I have to tell it how long to run, right? Now it can't be run forever, let us say. So we want to run it for, after it has collected 1000 traces or 1,000,000 traces. Suppose I want to give that information. Okay, I want to tell it, the device, that I get you started, but I want you to collect only 1000 or 1,000,000 traces. How do I do it? I can write to the device, okay, and that's what I'm going to do. Okay, I'm going to write to the device and set that parameter, whether it's 1000 or 1,000,000. Okay, that's what is going on here. Okay, so int s write is a code that basically sets the size of the buffer that has to be allocated in the kernel, how many entries has to be captured, and then you start the recording process itself. Okay, all that is being done here. Let's see how does it happen. So what is it doing here? This struct file, star file, is basically the /dev int s. Okay, and it's got a buffer. What is the buffer? The buffer is basically where I'm giving information about how many, the size of how many entries have to be captured. Okay, so what am I going to do here? If get user cbuff, right, or size less than 2, I'm just checking essentially if the data is valid. Okay, if my size is less than 2, for example, size is equal to 1, okay, or if I find that get user does not give me any characters at all, okay, this is basically error condition, I am not able to get anything useful, then something is wrong with it, I exit, okay. Get user is basically saying that somebody has given me this is a user space buffer, okay, and I am, instead of just saying get the character, I do not want to get directly, I want to go through a function called get underscore user, which is written by kernel, which is written and provided by the kernel people, okay. So I am going to use a careful return code which checks whether this particular buffer is a legitimate buffer, it is not some invalid piece of memory, whatever, okay, unmapped memory, those kind of things, okay. I am checking all those things. After checking it, I get some, if I find there is an error condition, whatever, I exit, okay, I won't touch it, that is it, okay. So again you can see it might have got one character. What is that? It is basically the, normally you will notice that many routines have, you can give some command line parameters, okay, and that command line parameter is s. You can say s is the size of the buffer or the number of entries I am interested. So you are going to run this program saying the name of the program followed by minus s followed by 1,000,000 or 1,000, okay. So what this get user is doing is getting that s followed by 1,000 or s followed by 1,000,000, that is what this is doing, okay. And once it has got the first character correctly, that is checking it, is the command line parameter, the switch, right, basically I have some options, right. So the option, is it s, for example, so it is getting the first option, okay, it is checking with s or capital S. If it is s or s means I am going to give the number of entries that have to be captured as a part of this tracing exercise, okay, that is what it is, okay. So then basically what is going on, I am going to copy the rest of it. See, the buffer is the thing that the user has given, it has confirmed to itself that this buffer is a legitimate buffer, that is why it came here, okay. Otherwise it will die here itself, it will return a e fault and out, if it is invalid buffer, etc. But it successfully came here, that means the character C was populated with one character, okay, so it got S, okay. So either it is S or it is some other junk value, okay, then in that case it just default, it just says something is wrong, okay. So it got the first character, it is somebody is trying to give it some size, okay, how many entries have to be captured by the tracing, okay. Now he is going to say copy from user from buffer plus 1, because character already, the first character says already, I am charactering from buffer plus 1 and I am going to get as many as this number of given by this size, okay, string size, okay, and I am going to put it in the kernel buffer. K buffer is something I defined, okay. Here I am defining 32-bit, and to make sure that I do not do any go beyond 32, I am making it min of that one, min of size of k buff 32 comma size minus 1. I am just always keeping sure that string size is less than is the minimum of size minus 1 and size of k buff, okay, just for safety. And then I am setting k buff string size equal to 0, that it terminates the essentially it terminates the value which is either 10,000 or 1,000,000 or whatever it is in characters, because I am giving it in character form on the console in the command line, okay. So basically what has happened is that you will find that k buff inside the driver has either 1000 or 100 whatever, okay, something, okay, and that is what I am going to do as scanf, and I am going to get it as number of entries, okay. So if the number of entries is wrong, then of course I exit, okay. So if the number of entries is fine, then because as a part of the write, I am going to do the recording, okay. But before I do that, that recording is going to be done here actually, okay. But before that, it may be that I am in some anomalous situation. No, the device drivers have to be very careful, okay. how you came to the situation sometimes may not know, because there is this user sitting there, the super users are there, and how many people have access to this device we don't know. Okay. So he is basically saying, I don't know the current situation, I am going to now get myself into a clean situation. Okay. So that is why I am going to say, if for some reason I am recording at this stage already, I don't know how it happened. Okay. I am going to say, okay, I don't know why it is now the way I am recording, I don't know why it is, because I was told to write and it is recording, something strange is going on, I don't care what it is, I am going to say I am no longer recording. That is what I am doing, but before I say recording equal to 0, I am going to clear interrupts and again now enable the interrupts, and again I have an event buffer. Okay. What is event buffer? Basically this is what is capturing events. What is an event here? Every interrupt is an event. So I am capturing some piece of information about it. I am going to have a corresponding event structure, that is event buffer. Okay. And I am checking whether this event buffer is already has some value, okay, which I didn't expect, because I am supposed to be doing, I am setting how many entries to be captured, right. So because of some reason I don't know how it happened, I am being careful here. Okay. I am just saying, okay, whatever happened, I don't care how it happened, I am going to free the structure. Okay. And I want to get to a clean state, I will start from there again. That is what I am doing here. I am going to free the thing. vfree is a particular call in the kernel, which is basically for freeing pageable kernel memory. Okay. Now in the kernel it turns out you can have unpageable kernel memory and pageable kernel memory. Unpageable kernel memory is that memory which cannot be paged out, because if you try to page it out, when you want it, it may be sitting in the disk and you might get into some great mess. Okay. So it turns out you cannot allow those kind of situations to happen. So there are two types of memory. Of course, there are many more types, but for the time being, just say that there are two types. So vfree basically saying that somehow some buffer EVT buff in virtual pageable memory in the kernel has been allocated, which I don't understand how it happened, but I am going to free it right now. That's what I am going to do. Now I am actually going to, now I know how many entries I should provide, because I just read the size here, right. I got the size of how many entries have to be there, right. On this particular write call, I am being told how many entries to capture, right. There was something here which I didn't expect, but I am just cleaning out of it. Okay. I am going to be in a safe situation. Now I am going to say, I am going to allocate that many number of events. So I can store that number of events, information corresponding to that. I am going to use something called vmalloc. Again, this is an example of pageable kernel memory. I am going to ask it to get me that amount, and that is going to be number of entries multiplied by size of this event. Okay. So event buff is basically some, you are getting the starting address of so many entries that have been allocated in the kernel now, and this is pageable kernel memory. Okay. And so for some reason it's, it has returned 0, that means that some bad stuff has happened. I don't know what it is. I am going to bail out again. Okay. Now this is a starting address, and basically I have to start recording it from next event, which I am going to start as a starting point, event buff. So next event is where I always keep putting stuff. So in the beginning it has to be at the very beginning, that is what it is. So after one event it will be pointing to the next one. Okay. Last event is where I should end. So I have allocated this much. Now I am putting saying next should start from here, and then it comes to the last one, stop there. That's what it is. Okay. Now once I have done all the initialization properly according to the information I have been told to use, right? Because previously I have been told to use this information, that I am going to see whatever is there in this buffer, get that number and allocate that number of entries. Okay. And that is what I have done all this here. Once I have done this, now I can now allow recording to start happening. This recording equal to 0 is just because I didn't understand why it is the situation the way it is. I am just getting to, I just want to be sane, that is all. Okay. Here is the case where I know exactly what I am doing. I said recording equal to 1. Now I move out. So the write code is basically, what is it doing? All it is doing is taking the some user has given a buffer. It could be wrongly given by sheer mistake, or it could be maliciously given also. We don't know how it happened. I want to sanitize it first here. All this sanitization is happening here in this code and this code. Once the sanitization happened, I look at the option, pick up that value of entries. Just again, this is just paranoia of some kind. Somehow I'm there, I don't know why it is there. Clean up, then allocate the thing, then start recording a walkout. Okay, so that's basically the write call. Okay. Now, what is the read call? Read call. Okay, I should just mention also one more thing. So, there is also in the write call there is a offset also. I mentioned that in all these devices there is a implicit pointer, right. When you do a read and write, I think all of you know that the implicit pointer gets updated. Okay. Now, in this particular device, it's not used, let's say, there's not much of use here, but all the same, you are doing the implicit pointer update here. That's what you're doing. Okay. Okay. So, I was talking about this part. Okay. So, basically when you use get user, put user, copy from etc., it does kernel user space address space check, just want to validate. Okay. Okay, so that's part of it. Okay. So, yeah. So, basically what we are doing in this example is when ints module is loaded, read, write, open, close operations of device map to driver routines. I think I already mentioned this. First, user writes to /bin test to set the number of trace entries using the command line and starts trace recording in an internal kernel buffer. So, this is what we looked at already. Okay. Now, what you have to do is using the command line, user runs a program that reads each entry and prints each trace. So, already it has collected that amount of information, right. Basically, you ask it to record it, you set up the thing. It's all recorded, kept in the kernel buffer. It's sitting there in the kernel buffer. Okay. So, now this pageable, that's why I'm not so bothered, because if that particular, once it has been done, right, let's say it's 1 megabyte, okay, it will get swapped out, it's okay, okay, it's sitting there, it will not be using real physical memory for it, okay. So, after some time, after I recorded all this stuff, I want to read it and print it out, okay. So, that's the program, and this program is here, that is user code. This is actual code which actually reads that stuff. So, it's sitting in buffer, right. And now I have to read it also. Okay. So, here is this is not driver code. This is not going to be loaded in the kernel. Okay, this is basically user code, and this is being run by you. Okay. This driver code before had to be loaded explicitly into the kernel. Okay. This one, it is a piece of code which is there, you compile it and you can start executing immediately. Okay. And what is it doing? It is first initializing something, basically it is opening some files, okay, and so that it has got 0 information, okay. That is why it is, in case it was there before, I have run it multiple times in the past, for some reason it has got some data, I want to truncate it, so basically the idea is that this file out CPU1, it has got all the trace events of CPU1. Out CPU2 is what? It's all the trace events of CPU2, what all interrupts came there, okay. And in the beginning after this particular code, this particular file should have 0 information, 0 bytes, okay. This also should have 0 bytes, okay, because I have not yet written it. Some stuff is already there in the kernel buffer sitting there, but not ready, I have not gotten into my file system yet, okay. It's staying in memory still, okay, virtual memory. That's what I have done here. And it is trying to see, this particular piece of code is checking for correctness. So it has got 2 stacks, CPU stack 2, okay. It's assuming 2 CPUs, okay. That's why there's 2 here, okay. So the thing is that reason why it has got a stack is because when I'm doing one interrupt, another interrupt can come in, okay. It's getting stacked, okay. It's trying to keep track of, it's checking whether the one interrupt coming in and exiting, for example, they are properly bracketed, okay. That's what it's trying to do, okay. That's why it is, the 0 is basically, if you look at push, int CPU, int val, okay, it's saying for assert, like basically it's, you can see what it's doing, CPU stacks 0 equal to val, okay. It's basically putting a -1 for the stack corresponding to CPU, first CPU, setting the value minus. So it's the bottom of the stack. The stack has got a bottom, it's got -1 at the bottom, that's what it's doing. Same thing with corresponding to the CPU 2, that also has got a -1. Now you read, if you read from the entries that have been already saved, okay. So basically all these are the entries, okay, and we got the entries and we are doing some checkings here, okay. Let's not, basically you want to see that you, if you read something, asking it to read 1 unit of that, it should be the same size that you read, okay, because size of E is basically the event size, basically that information about the one particular interrupt, okay. You are just checking that whatever you read, the first entry should be actually have the size of that event, okay. This is just all checking various kind of things, and basically what we are going to do is, I think we will have to look at some of this code in some more detail, but basically what this does is, it is, if there is no time corresponding to a CPU right now, okay, I am setting the time to be E10, because this basically started at some point, and how is it collecting the information? It's collecting the information by, if you look at it, see when I am doing a read, what is it doing it? It is using, okay, I'm not, okay, let me, since I have not done this part, okay, let's look at it one more time, okay. So, I think we will have to get into some details about what data was collected, how it was collected, right. So, as I mentioned, now you did the write, it has allocated buffers, it will start the recording, right. Now the interrupt start happening. So, when interrupt happens, what happens? The interrupt handler would have called p enter or p exit. Normally it is empty, nothing happens, okay. But in our case, because we loaded this particular driver, we have given it a specific thing, p enter and p is going to be enter IRQ, enter leave IRQ. These routines we have specifically done for this particular pseudo device driver, okay. And we have defined enter IRQ to be this and leave IRQ to be this. That means that on every interrupt entry or exit, these things will be executed. Let us see what it is doing here, okay. So, there are a lot of details, but let us just look at concentrate this one. This is something called RDTS call. This is basically a read timestamp call. In most architectures, there is something called a timestamp register, and this is updated every instruction, okay. So, for example, if your system is running at 2 gigahertz, right, and every instruction takes, okay, we will just simplify it, we will say it is this timestamp thing is incremented every clock cycle, let us just say that, just to make it simple. So, when you call this read TS call, it is recording the what is there in the timestamp counter, okay. And look at it, this happens to be actually this particular routine. Now, Linux specifically is very good at mixing assembly language code and C code, okay, because it uses GCC, and GCC has got very good support for mixing assembler language and regular C code. This is slightly tricky business, basically because you know that there is something called register allocation that happens, and if you arbitrarily put C code and assembly code together, they might be using the same registers and all those things. Okay, you have to get all those things consistently across. Okay, so there is some support in GCC to do all those things correctly. Okay, it's like delicate business, but they know how to do it. They've done it. Okay, so this is also another example. It basically tells you that there is in this value, right, next event is pointer time, right. What this assembler language code is basically saying is that read the particular value from RDTCS and put it there. This is basically the instruction. Okay, this instruction that is there in the assembler. Okay, and this basically saying this is a parameter that has to be updated. Okay, the parameter that is going to be updated is this. Okay, this may be allocated a register or whatever. That's something GCC is doing, handling it. Okay, so what it means is that once this thing is executed, next event arrow time will have the value of the read time, the real, it's going to have the timestamp counter in it. Okay, it has read it. RD is the read part, basically it's read it. Okay, so that's what so basically what is happening here is that you get the time and then you create a structure which basically says because enter IRQ, that event is actually entry into the interrupt, and then you are going to say that this event happened on this CPU, because this enter IRQ has, if you look at this P enter IRQ, it has got which IRQ and which CPU actually came as parameters. The same parameters are here, and those things are being recorded here, which CPU. Okay, and now it is saying that, remember that the buffer was here, this big, and you started from here, and you have to go to the next entry in the for the next update. Okay, that's what is being done here. Okay, we will look at the rest of it in the next class.